Hello, hello, aloha, bonjour, students of Maths C. This is another lesson on the logistic equation. This will be mainly on using Excel and how to graph the data that we get from a logistic model. So we'll look at the US population and the Chinese population, and we'll model both of them using the logistic equation, and we'll see if we can graph, we'll graph them against the census data, and we'll see how close our models are to those census data plots. Okay, so to get started, I thought we'll have a look at the task sheet. Here it is here. I've updated this, so the only change has been to task 3, which is about the Chinese population, and I'm guessing that no one's really looked at this task yet, so that's probably a good thing that I've changed it now. And it's just a subtle change, really. Previously, we had to come up with a logistic model to sort of emulate this population growth in China using technology, but now I'm suggesting we'll use these equations here to come up with the R&K parameters. These are the Verhulst equations for working out R&K. So that's the modification that's occurred there. Just know that task 3 is a small task. There's only 2 parts to it, and those 2 parts, the first part being coming up with the logistic model, the second part is graphing that logistic model against the census data. So that's really all task 3 is. You do a similar thing in task 2 with the US population, but there's a little bit more kind of analysis, and we look at various models for the logistic equation here. Okay, so without much more to say about this, I think we should start. So far I've done a video on question 5, showing you how to solve the logistic equation. So this differential equation here, converting that differential equation into this population model here. So that was question 5. I did a video on that. That was a pen and paper one showing you all the steps involved in solving that differential equation. So I guess we can have a brief look at question 6 here, which is using this US population data here to come up with a specific model for population growth. Okay, so you can see in here that the parameters, some of them are given anyway. So the carrying capacity K is given at 470 million, and the initial population at 3.93. So we're going to be using this piece of data here as the initial population. So we're going to say that 1790, the year 1790, is times 0. Now we're looking to emulate Verhulst's model, so we need to use data that was available to him in his lifetime. So that means anywhere up to 1840. So I think for question 6, well, I've sort of done this already. I'm not going to go through the steps in great detail, but I will show you here what I've done. So let's bring this over here for a second. So here's the logistic model that we figured out in question 5. Here's the parameters that are suggested here in question 6 here. So the initial population of 3.93 and the carrying capacity of 470. Now, using those 2 parameters there, we can work out this C parameter. Now, if you remember back here that we use a C parameter as part of our main model here, really just so it's easier to write. This thing looks a lot nicer written in this form, rather than having to, in place of C there, have all of this business. So C doesn't mean anything really. It's just a convenient way of simplifying, these 2 parameters here, and how they sit in the model there. So C is a simple thing to calculate. It's just the difference of the carrying capacity and the initial population divided by the initial population. And so putting the numbers in here, we figure it out to be 118.59. Now that goes in here. K goes in here, and then what I've done here is I've chosen another point in the data set here. So remember, we need to choose data within the range of 1790 up to 1840 in the lifetime of Verhulst. So I've conveniently chosen this one here at 1840, and so 1840 is 50 years on from 1790, and so T will be 50 and P will be 17.07. So putting those numbers in, so this is the model here. We substitute in for P, for K, for C, and for T. The only unknown now is R. So now it's a case of rearranging this and solving for R. Now there's a few steps involved there. I'm not going to go through them right now. This is something you should be able to do. It's really, some basic algebra where we cross multiply. We can swap these two things over. We're going to have to apply some logarithms to free up the exponent here where the unknown is. And eventually we'll get to R, and R should be around about this value here, which is 0.0299, so about 2.99% annual growth, or roughly about 3%. Good. So that's really all we have to do for question 6. And in the end, once we know R, then we write the model out with all those parameters substituted in. So the 470 for the K, the 118.59 for the C, and the negative 0.0299 for the R. Okay. So remember that don't remember, but know that that negative there for R is not suggesting it's a negative growth rate. It's really a negative exponent because we have it as part of the denominator. If we were to do a bit of maths on this, we could move this term back up into the numerator position. We'd find that would become a positive. So that's the only reason we have a negative exponent, is because we're dividing by that thing there. So okay, so good. That's all you have to do for question 6. So I've pretty much sketched it out for you. I just haven't put in the full details of how to go from here to here, which I'll leave that for you to figure out. Okay, very good. So question 6 is done. Now question 7, we're going to now use this model here, and we're going to generate some data from it and graph it, and then compare the data that we get against the data that we have here. Now we're going to extend it a bit. So this model is really fit for the time period from 1790 up to 1840. We're going to extend it though up to 1940. So we're going to push it forward another 100 years. Okay. And so let's look at the things that we have to do here. We have to compare the predicted population against the actual population. So the predicted population will come out of the model here. The actual population, well, we have that sitting up here. We do it in a spreadsheet, and we do it over each decade, so every 10 years. Then we're going to calculate the percentage error. So comparing the numbers we get out of this model against the numbers that we have here. So that's just a simple comparison. We'll do that in Excel as well, and then we'll graph the two together. So that's what it says here, to plot. So simply put, we're doing this. Okay. So here's the model population. Here's the actual population. So I've just taken this data here. Notice it's in these are all in the millions. So from 3.9 million in the year 1790. If we go all the way up to 2010, it's about 308.7 million. So I'm doing everything in millions here. They're just nicer, easier numbers to work with. So if we think of everything as being in millions, we can just work with these numbers. So there's our model population. There's our actual population. So these numbers here are really just rounded versions of what you see in here. The model population, well, this works off the formula that we came up with over here. So this formula here. So let's see how this all works. Okay, so I've set this up with my parameters up the top here. So these are all fixed. So P sub 0 is the initial population. R is the rate of growth. Now that's not what I had here. What I have here is 0.0299. So I'm going to change that now to 0.0299. It's better. And the carrying capacity, we said that was 470 million, didn't we? So that's 470. Okay. and the C value in here. So this is just a simple formula which calculates K minus P sub 0 divided by P sub 0. Done. And so that's all good. And then the model population. So this is the logistic model in action right here in the spreadsheet. So if we have a look, you can see that this form here is now recreated up here. So let's follow this through. So I've put in equals E dollar symbol 4. So E4 is this cell here. So no, it's not. It's this one here. It's the blue one. So that's my carrying capacity K, right? So we're saying K here divided by, in brackets, 1 plus E5, which is C, times by E to the, so in Excel we use EXP for the exponential function. So EXP in brackets, negative R, which is E3, and then times by time, and time for us is over here in the D column. So I'm starting at D9, that's at time 0. You can't see that because it's behind the formula there. Now if you have a look at everything in this formula here, you can see all the parameters, E4, E5, E3, all these things here, they're all fixed or they're all anchored, and we do that using the dollar symbol. Okay, now the reason we need to fix them or to anchor them is to make sure that as we apply this formula down through the column here in this way, we want to make sure that in each row, hang on a second here, now that's how you stuff it up. Let me fix that up. Okay, so we want to make sure if we go to this row here, we want to make sure that these parameters are still coming from the same place, so they're fixed. Okay, the only thing that is a variable is the last entry here, which is the T entry, the time. Okay, now that is a variable, so we want to make sure as this formula is being applied all the way down, it's pulling the new T value from here. Okay, and that's doing the job there. So if I use my control tilde combination on the keyboard, you can see all the formulas here. Okay, now time, that's just working off the years. So I'm basically converting my years to a reference times 0. So 1790 references as 0. So that means, and these will go up in 10 years. So basically, I could just string this down as being 0, 10, 20, 30. I'll get the same thing. The most important thing here, of course, is the formula in here, which is the logistic model. These numbers here were copied from the task sheet. Okay, and here's my error formula here. So we could have a quick look at that as well. So how do we calculate error? So this is a very compact, simple way of doing error. What I've done is I've basically, ABS is the absolute value, right? And so what I'm doing is getting the difference between these two population values. So one is obviously from the model, one is the actual. So we get the difference of those. Now it doesn't matter, which way you do the difference. In some cases, one might be bigger than the other, or the other might, the model estimate might be bigger than the actual population, or vice versa. We don't care which is bigger. We just want the absolute difference. So if the difference between the two is a negative number, we take it as a positive number. Okay, so we're just looking for the gross difference between the two. And so that's what the ABS function here does. It just takes the absolute value of the difference, turns it into a positive number. So once we have the difference, then we divide the difference by the census value. Okay, and that gives us a percentage error, if you like. Okay, so it's the absolute difference between these two divided by the actual population. Okay, and you can see these are all in percentages. So what I've done is I've calculated this value here, and then I've converted them to percentages. You could, as an alternative, just times it by 100. That would do the same thing. Okay, now, good. So we have all our data here. We're comparing the logistic model data to the actual data. Now we need to graph it, and that's what I've done over here. So a quick way to graph this, so I've already got it here, obviously, but I'll recreate it just quickly. Is to, it's best for the time axis here that we use the actual years, not the time since, although it doesn't matter if you use the time since 1790, but I'm going to use the actual year. It just looks better on the graph because we can see exactly what's going on. So let me highlight the time, and then I'm going to highlight using command, or if you're on a Windows device, computer, you'll use control, and I'm going to highlight these two columns here. Now that should be enough for Excel to know that I'm going to graph, this is my x-axis and this is 2y series. Okay, so let's go into charts, scatter, and I'll do the dots, so no lines connecting the dots, just the dots, and you can see I'm getting the same graph here. Now if you prefer to have the lines as I have here, connecting those dots up, and that's not a bad thing to do, you can change your chart type to, if it's going to let me. Okay, it's not going to let me. Why is it not going to let me? It's weird. Maybe I need to highlight. Yeah, okay, normally that would work, never mind. Alright, so if I was to do that again, I could just do that one there with the connecting lines, and that's basically what you see here. So the only difference between these two graphs, of course, is that I've put in labels here, I've put in a title, I've put in X and Y labels, and I've also given names to each of the series. And to do that, it's just a simple case of going in here, right click, select data, and just naming the series, as you see there. Okay, good. Now, so let's have a think about where we're at now with this assignment. We've looked at question 6. We've just had a quick look at question 7. We've calculated the percentage error. We need to comment on the accuracy of our predictions. Now, if we go in and have a look at these percentage errors here, you can see that the error is quite low up until about 1870. Now, remember that Verhulst was around between 1790 and 1840, so we're using his ideas in developing these models. But we're extrapolating well beyond 1840. We're going 100 years beyond, and you can see what happens once we get to the late 1800s. This percentage error really starts to increase, and you can see it in the graph as well. You can see the divergence between the census population and the logistic model. So our logistic model is suggesting that population will keep increasing. Here, it almost looks like there's a bit of a tapering off, or an inflection, okay, which is one of the features of the logistic model, in fact, that it does inflect and sort of head back towards a kind of a maximum population, the carrying capacity, that is, of course. Now, what we see here is not actually an inflection point, and when we get to question 8, we'll sort of look at the data beyond 1940. We'll look at the data up until current times, and we'll notice that this inflection here is interestingly to do with some other factor that happened in the 1940s, something like a world war and a depression that followed. Well, there was a depression that was before the World War, so those factors would have contributed towards that slump in population growth in that time period. So, okay, so that's talking about the percentage error. Comment on the accuracy of the prediction. So accurate up until maybe the sort of the mid 1800s. Beyond that, not so accurate. Now, just to add some weight to what I just said there, I want to reference a document which you have. So if you go into Schoology, you'll see there's this one here, Verhulst document for task 2, and let's have a quick look at it. Here it is. So you should have a hard copy of this as well. But if we go through the literature here, we'll see what Verhulst. This study here is really looking at the Belgian population, and you can see his logistic model here. This is the same one that we're using. It looks a bit different, but it's essentially the same. And this is looking at the population of Belgium from 1700 up until now. The data points correspond to the years so around the sort of the early to mid 1800s. and here's some US population data as well. Now, just somewhere down here, there's an important sentence here that I want to point out to you. Here it is here. So this is on page 38. Page 38. Yes. And so what's it say here? It says, as the populations of Belgium and France have in the meantime largely exceeded these values of K, we see the logistic equation can be a realistic model only for periods of time of a few decades. Okay, so really, I mean, that might be a little bit out of context, but ultimately what it's saying is that we can't expect to extrapolate beyond, a few decades, within the data that we used, and get accurate results. So I think the limitations, one of the main limitations of the logistic model is that it can only be used over, short time periods. And another point I should make, actually, which is probably just as important, and that is this idea that the population or the rate of population growth is a constant. Now, in our model, we've said as much. We have a look at our model here. We fix the rate, at about 3% per annum, and we're saying that is the case through that whole time period from 1790 up to 1940. Now, I'm just going to show you something that will show you otherwise. So here's a website here. This is just US population or some US history. The URL is here if you want to check it out. So it's got the US population data from 1790 up until the year 2000, and if you compare the values here for population, you'll see they're very similar to the ones that we're using. But more importantly, over here you can see what the rate of growth is. Okay, now these are percentages over 10-year periods, so it's looking at the increase over a 10-year period. So to give you an example, if we go from 1820 to 1830, you can see that the population increases from about 9.6 to 12.8. So it increases by about 3.2 million. And if you think about it, 3.2 million is about a third of 9.6, roughly. And that's reflected in this percentage here of 33% over 10 years, of course. Now, if we want to get an annual rate of growth, then we just divide this by 10. So 3.3. So, 33% over 10 years, 3.3% over 1 year. So with that in mind, we can scan through and look at all these percentage increases, from 1790 up until the year 2000. And what you'll notice is that in the time period that we were focusing on initially, from 1790 up to 1840, the annual population growth rate is somewhere between 3.5, maybe a little bit less in some periods. So it's never below 3.27. It drops below that once we get to here, 1870. Now, that would be interesting to know what's happened in this time period here, to see that sort of, sudden drop in rate of growth. I mean, the rate of growth, the population's still growing, but just not as rapidly. So essentially, the rate of growth is not a constant, and you can see that here. Now, if we look within a few decades, so if we say look from the year 1790 up until the mid 1800s, we could safely say that the population growth rate is pretty constant. About 3.3% or maybe 3.5. If we look in the last century, so early 1900s, you can see it's around 20. It's around 20% there, and then it drops. It drops dramatically. So 15. Well, we're really looking 1.5, aren't we? 1.5, 1.5. So really, from 1920 through to 1980, So we could safely say that 60-year period, the rate of growth is around 1.5. I think that's fair to say. So that's certainly something that you should talk about in your write-up. And if we go back to the task sheet, which is somewhere here, we just drop this down, drop that down, drop that down. So the task sheet is here. So let's have a look where we should talk about these things. Possibly in here, comment on the accuracy of your prediction. So you can talk about the assumptions made. So the assumption that the rate of growth is a constant, well, actually it's not, and you can see over time it changes. Within a short period of time, it's fairly constant though. So our models are valid for those short periods of time, but if we extend them over longer periods of time, they're less valid.